This video is all about conjugate acid-base pairs, how to identify these conjugate pairs based on chemical formula, how to assign and compare a stronger versus weaker conjugate acid, and what this comparison means for the corresponding conjugate bases regarding strength and stability. We identify a conjugate acid-base pair within an equilibrium as being on different sides of the arrow. One conjugate is a reactant and the other conjugate is a product. The conjugate acid is the more protonated form, which means it has one more H and one more plus compared to the conjugate base. The conjugate base is the more deprotonated form and has one less H plus compared to the conjugate acid. The chemical formulas basically look the same, except for the difference of one H and one plus. Worth repeating here is that the conjugate acid is always the protonated form, and the conjugate base is always the deprotonated form. This is actually a very big deal when it comes to comparisons. A stronger conjugate acid undergoes increased dissociation compared to a weaker conjugate acid, and as such will have a higher value of Ka. This higher value of Ka corresponds to a lower value of pKa. Stronger acid equals lower pKa. So how does a stronger conjugate acid relate to its conjugate base? A stronger conjugate acid is more likely to dissociate, which means it's more likely to form products. If forming products is more likely, then this means its conjugate base product is more stable because it formed more readily. Because this more stable conjugate base is stable, it is less likely to react as a conjugate base to accept an H+, which is what bases do. If the conjugate base is less likely to accept a proton, then it is by definition a weaker conjugate base. A stronger conjugate acid has a weaker and more stable conjugate base. The equilibrium is more favored towards that acid's products. A weaker conjugate acid is less likely to dissociate, which means it's more likely to remain as a reactant. When it dissociates, it forms a less stable conjugate base, which is more likely to react as a base in the reverse reaction and accept an H+, making it a stronger conjugate base. Both of these arguments, acid less likely to dissociate and base more likely to react, result in the equilibrium for a weaker conjugate acid favoring its reactant side. When we say that equilibrium favors reactants or favors products, we are talking about relative to the starting point of the particular conjugate acid, not an absolute reactants versus products. Before we talk about pKa's, there are a couple important points here. First, a pKa can only correspond to an acid, which means whenever we are using a pKa for a comparison, we must assign the pKa to the protonated form of the conjugate acid-base pair. On the other hand, when we talk about a conjugate base, we must refer to the deprotonated form of the conjugate acid-base pair. With that said, a stronger conjugate acid has a lower pKa compared to a weaker conjugate acid, and the favored direction of equilibrium, based on what we've already said, will be away from the side with the stronger conjugate acid and toward the side with the weaker conjugate acid. The favored direction will also be toward the side with the more stable conjugate base, which is by definition the weaker base. If the equilibrium is favored away from the lower pKa, then it must be favored toward the side with the higher pKa, as there will only be two pKa values to compare in a given equilibrium. Finally, all of these arguments are consistent with the equilibrium favored toward the side with both the weaker conjugate acid and the weaker conjugate base. It can be easy to get lost in some of this logic, so it is important to lay it out step by step as you compare conjugates and make predictions. In our first example, we are setting out just to identify the conjugate acid-base pairs in the equilibrium. Remember that we're looking for similar formulas that differ by an H and a plus. That means the atom H and a charge difference of a plus. So in looking for similar formulas, I can identify HNO2 and NO2 minus as being similar, and H2O and H3O plus as the other pair. So in my first pair, the more protonated form will be the conjugate acid, and more protonated means it has the extra H plus attached to it. So the conjugate acid in this pair will be the HNO2 because it has one more H and one more plus compared to nitrite. So nitrite will be the conjugate base. In the other pair, I have water and hydronium ion. Hydronium ion is the conjugate acid because it has the extra H and plus compared to water, which will be the conjugate base. In this example, we are doing the same thing. We are identifying the conjugate acid-base pairs. So I find HF and F minus. The chemical formulas only differ by an H and a plus. The HF has one more H and one more plus, so it will be the conjugate acid, and fluoride, F minus, will be the conjugate base. The other thing to notice is, as we said earlier, one conjugate of the conjugate acid-base pair will be a reactant and the other one will be a product. And what we're seeing here is consistent with that. So our other conjugate acid-base pair will have to be the nitrite and the nitrous acid. So those two are connected. The HNO2 has to be the conjugate acid because it has the additional H and plus compared to nitrite, which will be the conjugate base. In our next example, we are going to use pKa values to make some comparisons. So the first question is asking which one is the stronger conjugate acid between HNO2 and HF. So I'm going to note the pKa for each one. Remember, a pKa must apply to a substance acting as an acid. So the pKa for HNO2 is 3.34, and the pKa for HF is 3.46. So the question is asking, based on that, which is the stronger conjugate acid? And if we simply compare the numerical values, HNO2 has a lower pKa, HF has a higher pKa. The lower pKa corresponds to the stronger acid. So HNO2 is the stronger acid. The next question is asking, which conjugate base is stronger? Now we've just used the pKa's to identify the stronger acid, and the acid has to be the protonated form. If we look at the deprotonated form, in other words, if we remove an H and a plus, then we have NO2 minus and F minus. So these are the conjugate bases. The stronger acid corresponds to the weaker conjugate base. And that means that fluoride must be the stronger conjugate base because it corresponded to the weaker acid. And the last question is asking about the more stable conjugate base. So you can see here, when we're talking about the conjugate bases, we have to add a proton, add an H plus to get the conjugate acids, and then we can use the pKa values of the conjugate acids as a means of comparison. We kind of worked backwards, starting with the conjugate acids here, but it is important to see that connection. We cannot apply a pKa directly to a conjugate base. So just as a recap, we started with the conjugate acids. We identified the one with the lower pKa as the stronger acid. We then looked at the conjugate bases and identified the weaker conjugate base corresponding to the stronger acid. So because of that, fluoride ended up being the stronger conjugate base. Now we're after the more stable conjugate base. The weaker conjugate base corresponds to the more stable conjugate base. And that's because a weaker conjugate base is less likely to react and go in the other direction because it is more stable. So these comparisons always hold. So the answer to this final question is that nitrite is the more stable conjugate base. And just for completion, I'll fill in for fluoride as being the less stable conjugate base. These can be a little bit confusing, so it's a good idea to practice with several examples and go through the logic systematically each time, and then you'll be able to internalize that logic and it will make more sense. So in this equilibrium, we're going to use pKa values to predict in which direction the equilibrium is favored. We've already done most of the work in the context of the other problems, but I'm still going to take it from the beginning, and you'll see some of that repetition, and hopefully it's a little bit more familiar because we've gone through some of this work already. So I'm first going to identify my conjugates, and I'll use the same color coding that I used earlier. So we have our conjugates. The next thing I'm going to do is write the pKa value for each acid underneath the acid formula. So the pKa value for HNO2 is 3.34. So I'm going to write that right underneath the nitrous acid. And the pKa for HF is 3.46. HNO2 is the stronger acid because it has the lower pKa. HF is the weaker acid because it has the higher pKa. Notice we can only talk about pKa's for the protonated form of the conjugate acid-base pair. We also know that the stronger conjugate acid produces the weaker conjugate base, and that the weaker conjugate base is also the more stable conjugate base. So because HNO2 is the stronger acid, NO2 minus must be the weaker conjugate base, but also the more stable conjugate base. And fluoride is the less stable conjugate base. This argument about the stability of the conjugate base comes up over and over again in organic chemistry, and understanding it now will help you out a lot when you get to those courses. Let me also just add for nitrite, which is the more stable conjugate base, it is the weaker conjugate base, and fluoride is the stronger conjugate base. So the stronger conjugate acid is more likely to dissociate to form products. Our stronger conjugate acid is HNO2, and it is more likely to dissociate and form its products. That means that we expect the direction of the equilibrium to be favored toward reactants. And this brings up the question, does this make sense with the other things that we've learned? And it does, because the other thing that we learned was that the equilibrium is favored towards the weaker substances, the weaker conjugate acid and weaker conjugate base. So our prediction that this equilibrium is favored towards reactants is consistent.